Hello, calculus students. Welcome to another online lesson. We are continuing our unit on integrals or antiderivatives. We have two goals for today's lesson. We're going to first figure out how to find C values. We talked about this a little bit last class, but I'll review it here in the video. C values meaning that when we do our antiderivative, there's always the possibility of a constant being added or subtracted to the end. And we're going to talk about how to find that constant or C value. Also, we're going to talk about additional rules for integration that'll hopefully make our lives easier or allow us to solve slightly more complicated problems. So to start with, let's look at this first example where I have a function passes through the point 1, 4. They give me the derivative, which is 3x squared minus 2x plus 3. I want to write the equation for the original, the y, in terms of x. So let's start with that. So I've got y equals, I'm going to take my old exponent of 2, raise it up to 3, but then I have to divide that new exponent. There was already a 3 there, and 3 divided by this new 3 gives me 1. So 3x squared becomes x to the third power minus 2x. Well, my x is going to get raised from an exponent of 1 to an exponent of 2. And then I divided 2, but there was already a 2 there, a negative 2 in fact, and negative 2 divided by 2 gives me negative 1. So I have negative 1x squared, or negative x squared, plus 3. Anytime there's a constant, you simply add an x on, and then we have our C value here at the end. Again, to check our work, we could always do our derivative and make sure that we end up with what we started with. Derivative of x cubed becomes 3x squared, negative x squared becomes negative 2x, 3x becomes 3, and our constant would become 0. Now, we'd like to find out what C is. There's a lot of variables here. We have y, x, and c, but they gave us a point. If we can plug in this x and this y, 1 and 4, there's only one variable left, and then we can solve for c. So y is going to be equal to 4. 1 cubed is our x is 1, so I plug that in. We have 1 cubed minus 1 squared plus 3 times 1 plus our c. Well, 1 cubed is 1, as is 1 squared, and they're subtracting, so those cancel out. And then I get 4 equals 3 times 1, or 3, plus c. Subtract 3 from both sides, and I get c equals 1. Now again, our goal wasn't to find c, our goal was to write the equation. So the final answer to our equation, I go back to what I started with and replace my c with a 1. So y equals x cubed minus x squared plus 3x plus 1. So again, what do we need to find our C value? We need to have an input and an output, a point, an x and a y, and then we can plug that back into our equation to solve for C. This is only, we only have to worry about C anyway when it's an indefinite integral where there aren't boundaries. So if there aren't boundaries and we have a point, we can find what the C is. If there aren't boundaries and we don't have a point, we have to leave the C in our answer. For the second part of our learning intention, we wanted to talk about other properties of integrals. So I'm going to talk through each of these. We'll look at a little example and then call it a day. So the first one's pretty obvious. It says that our boundaries are a to a. So when we do our fundamental theorem of calculus, you're going to end up doing the antiderivative of f. You're going to plug in an a, and then you're going to subtract that exact same thing. And that, of course, is going to be 0. So that one is obvious. Then our next one says if we normally go from b to a on our boundaries, or if we were to, it's just the opposite of going from a to b. And we can see that, like, let's say that after we plugged in our boundaries, we had a 2 as one of our values, and for the other boundary, we plugged it in, we got a 1. If we subtract those, we get a value of 1. Now, if we reverse those, plugged them in the other direction and subtracted, I would get the opposite of that. So we can reverse our boundaries. All we have to do is put a negative outside of our integral sign. Our next one, we see that there's a constant or coefficient in front of our function, and we are allowed to just pull that coefficient outside. The reason that works, as we know, coefficients just sort of hang out when we're doing derivatives and integrals. We don't really have to worry about them. And so when we do the fundamental theorem of calculus, again, going back to that previous example, let's say I had 2 minus 1, which equals 1. But let's say there was this coefficient here. Well, if I kept the coefficient in, let's say our coefficient was 3, I would have 3 times 2, and then I would have 3 times 1, because it's 3 times bigger than our function, which would give me a 6 minus 3, which is 3. But if I just went back to the original value of 1 and multiplied that by that same coefficient of 3, I still get 3. So what does that mean in the long run? Anytime you have a coefficient, you can just bring it outside and do all your work without it, and then just remember to multiply it when you're all said and done. This one's nice if you have two functions in which you can do the antiderivative of, and this really even works with 2 or more. You can break it up into separate integrals. Again, this is great for when you have very complicated integrals. You don't have to do it all together. You still have to do the whole, plugging in the boundaries, fundamental theorem of calculus, subtract. But once you have those answers, then you can combine those together. And that works for both plus and minus. So break up two functions, or functions being added or subtracted together, into two separate integrals. This one looks a little confusing if you read it at first. It's just a constant, not a coefficient, but a constant in terms of x. So it's just c dx. And we know that the antiderivative of c is always just going to be cx, or cx plus c. And when we plug in our boundaries, it'll be c times b minus c times a, which we can factor out of c, so it's just c times b minus a. So if we just subtract our boundaries and multiply by c, we get our integral. And for this last one, it says if we have a boundary that goes from a to b, and then the same function has a boundary that goes from b to c, we can combine that into one integral where we go from a to c. And really, it should work backwards as well, but that's kind of the idea. So here's an IB question. It gives us an integral. It does not define our function. And it says the integral from 1 to 3, so it's a definite integral defined, it has boundaries, from 1 to 3 of the function g of x in terms of x equals 10. Deduce the following. So what do we have here? We've got from 1 to 3, 1/2 g of x. 1/2. What is 1/2? That is a coefficient. So as we learned, we could rewrite this whole thing with the coefficient out front. So that would be 1/2 integral from 1 to 3 of g of x dx. Now let's do a substitution. We know that from 1 to 3, g of x d of x equals 10. So all of this stuff, circle here in green, all of that equals 10. But we have a 1/2 in front of it, so our final answer for part A would be 5. For part B, we have two functions. One is g of x, one is just this nice little guy, 4. And we know that we can break this up into two integrals. So I have the integral from 1 to 3 of g of x dx, and then I have another integral from 1 to 3 of 4 dx. And since the original functions were being added together, these integrals are going to be added together. Well, I already know that the integral from 1 to 3 of g of x dx equals 10. So I can replace this whole first integral with 10, plus now I have the integral from 1 to 3 of 4. Well, that's that constant one. And the rule here was that we can take the 4 times the difference of our boundaries. So 3 minus 1, which is 2. 4 times 2 gives me 8. And so this is 10 plus 8, or a grand total of 18. And that's the idea of some of the ways that we can use properties of integrals to solve some more complicated problems. We'll look at one or two more similar examples in class next time. But until then, you can take a look at some problems on page 470, and we'll see you next time.